Welcome to Mastering Solutions. Let's make a list first of the information that they give us on this. They tell us that we have a very thin oil film with an N of 1.25, and it's sitting on water, and that of course is an N of 1.33. And we want to know what is the thinnest film that produces a strong reflection for green light. So our lambda is going to be 500 times 10 to the negative 9 meters. And we want the thinnest film for a strong reflection. So that strong reflection means constructive interference. And the thinnest possible film that we can have for constructive interference is going to be an M of 1. You'll see in a second, we talked about this in the last question too, but if we have an M of 0, then that would give us a film thickness of 0, which of course we can't have. We need some sort of thickness to it. So M is the smallest M value that we can use. And we're looking for T, what is the thickness? So since they're using constructive interference, we need to find how many phase changes do we have first. Let's draw a picture. So here is our thin film, and that's sitting on water. And then we're going to have light that will come in, and some of it will get reflected off. And we're going from a lower index of refraction of 1 for air. And here is our thin film, which we said is 1.25. And then this is, of course, water, 1.33. And so we're going from a lower index of refraction into a higher index of refraction. So when this comes in, now we're going to get a phase change right there. Now we're going to get a phase change right there. Some of this will get reflected out. And then now we're going from another lower to higher index of refraction. So we're going to get another phase change right there. And then that will go in. And so now for our phase changes, we have 2 phase changes and we need constructive interference. So we're told in the book that the equation that we'll be using for that situation is 2t is equal to m times lambda over n. Now to solve for t to isolate it, we can divide both sides of the equation by 2. So we'll have t is equal to m lambda over 2n. And now we have all of our information, so we just have to plug everything in. So m, as we talked about, is going to be 1 times lambda, in this case, is 500 times 10 to the negative 9 meters. And then all that is divided by 2 times the index of refraction. And in this case, our thin film is 1.25. So now when we go here, we have 500 times 10 to the negative 9 divided by 2 times 1.25. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 200 times 10 to the negative 9 meters, or a thin film thickness, the thinnest in this case for a strong reflection of green light at this wavelength is 200 nanometers.